So after that, what happens? After that, the belief is that there's a period in the universe where the universe consists entirely of hydrogen and helium, nothing else. A little bit of deuterium, tiny amounts. And it's completely dark. There are no stars, nothing. And in this period, slowly, very slowly, you start to build up the first galaxy. And the first galaxies form about 400 million years after the Big Bang. There's a long period from 400,000 to 400 million when there's basically nothing. I mean, there's just hydrogen atoms slowly moving towards each other. And then the first stars form about 400 million years ago. And then slowly outwards, as the universe expands, you form more and more and more galaxies until you see today the galaxies that we know and love. And at some point now, in the last 20 years, we believe there's evidence that the universe actually accelerates. So I said that the universe is expanding. The picture that we have of the expanding universe is that, if I throw, let's say, if I start with some expansion, with some velocity, and I throw this thing up, it falls back to the ground, right? It falls back to the ground because of the gravity of the Earth. Now, suppose I threw this thing up, and instead of falling down, it just kept going upwards with an acceleration. Remember, if I throw it up like this, it's decelerating. It's going up slower and slower and slower, and then stopping, and then turning back. Suppose I threw this up, and it kept accelerating. It kept going faster and faster. That would mean that the gravity of the Earth is repulsive. The Earth is basically pushing away this object. And that happens in very strange circumstances, and we'll talk about that. But the belief is that the universe over here is actually accelerating. That is surprising because you can think about this expansion as exactly the same way as you think about something thrown up. This is an expansion, and there's a huge amount of matter inside the universe. So the expansion has to do work against this gravitational pull of the matter. So you expect the expansion will go slower and slower and slower, and slower and slower and slower. But what seems to be happening today is that the expansion has gone slower at the beginning, and then now suddenly it's speeding up. And that's the reason we believe that there is a strange form of energy called dark energy. And I'll talk about that right at the end. So that's the picture that we have. These are the various cosmological epochs. There is the extremely early universe, which might be called the particle physics epoch, roughly 1 second after the Big Bang. There's nucleosynthesis, where you form helium and deuterium and so on, 1 second to 20 minutes after the Big Bang. There is something called the epoch of recombination, because hydrogen atoms are formed there by the recombination of protons and electrons. That's about 400,000 years after the Big Bang. That produces the cosmic microwave background radiation. Then there is a period called the Dark Ages, no galaxies or stars, up to about 100 million years after the Big Bang. Galaxies form and evolve from about 100 million years to today, 3.7 billion years. The first stars switch on somewhere about the same time, 100 million years. There's a funny epoch called the epoch of reionization, in which the first stars ionize the universe. And that happens roughly 200 million years after the Big Bang. And then, about 8.5 billion years after the Big Bang, this funny dark energy dominates the universe, and the universe accelerates outwards. So that's a picture, that's kind of a single slide view of what we think the Big Bang is like, or the universe is like. You want to?
这张有好多的名词哈，我简单讲一下，就是这张就是宇宙的历史了啊。那一开始的时候都刚刚讲，就是一些最简单的基本的粒子，在1秒钟左右，然后就很高热嘛，所以这些基本粒子会产生一些核融合啊，所以大概有几十分钟的时间。然后刚刚讲说，大概前30几万年呢，都是这个属于这个还是游离的状态啊，就是刚刚讲光不透明的状态，那个时期就产生了这个宇宙微波背景辐射。再从这边开始啊，它后面有一个括号写 Z 啊，这个 Z 就是天文学家用来量红移的，就他刚刚讲红移的这个波长移动的程度啊，跟这个速度是有关的。啊，那个 Z 各位现在不用管它，它就等于是那个当时回过来的时间是一样的，这两是一样的意思。所以宇宙是38万年的时候，我们从这边看到它的后退的速度快到 Z 呢是等于1000亿，是这个意思啊。那到后面会有一段时间会 被叫做 Dark Ages， 他当然是故意用这个历史的这个黑暗期来表示，就是那段时间恒星没有形成，所以宇宙中没有手电筒，没有光芒，没有光源，所以那段时间是这样。后来恒星慢慢建构在一起，组合在一起，就做成了星系，星系就开始演化，一直到今天还在演化。那第一颗星跟星系当然是同时的，就做出来了。大概整个宇宙1亿年的时候，恒星做出来以后，它发出来的光芒就会把旁边的气体又游离了，所以会有一个再游离的这个时期啊，下面写的第一期那个时间。然后到了我们现在倒回去看，没有很久以前，我们这个宇宙呢，就不光是辐射啊物质，而是开始有谢谢，然后开始有这个暗能量是主宰。他刚才举了一个例子，就是说，如果一个东西这样散开来的话，由于是彼此之间万有引力的关系，这些东西应该都要减速的。就好像我今天拿一大堆东西往上抛，这些任何一个东西一定都要减速，因为地心引力是向下，所以这个宇宙膨胀了以后，照理说应该要减速。可是过去10年的一个很意外的发现，就是我们发现宇宙好像不是，不但没有减速，而且反而是在加速的膨胀，所以才想到说宇宙中间应该有一股我们不知道的能量啊，在不久前它才扮演了比较重要的角
So
色。
these are the 2 biggest pieces of evidence for the Big Bang cosmology. The first one, and funnily enough, they both came from 2 people really, Ralph Alpert, George Gamow. Alpert again and George Gamow. And they both came just after the Second World War, 1948 roughly. The first one is that, remember I said over here that at some point you will actually form helium-4, helium and deuterium, about 2 or 3 minutes after the Big Bang. The helium and deuterium must form everywhere in the universe, which means that if I go out and measure helium, the amount of helium in the universe, I should see the same amount everywhere. If I measure here, wherever I look, I should see the same amount of helium. I should see the same amount of deuterium everywhere. And based on the theory, I can predict how much helium there should be, how much deuterium there should be. I can actually predict this from theory. And so for the last 30 or 40 years, people have been trying to measure the amount of deuterium, helium, and lithium in different parts of the universe. And if this Big Bang nucleosynthesis model is correct, we expect completely uniform abundances of helium and deuterium in different galaxies. And deuterium is actually really special because we don't know of any other way to produce deuterium in the universe, in galaxies, except via Big Bang nucleosynthesis. So deuterium is fundamental to these predictions. The second thing, of course, is that we said at very early times the universe was really hot and the atoms were broken up into protons and electrons. And as I said, because light is electromagnetic radiation, it interacts with the electrons and it scatters, it goes all over the place. And then once the universe is cold enough, 400,000 years after the Big Bang, the protons and electrons recombine, they form neutral hydrogen, and the light comes out. So the prediction is that you should see this light everywhere, in whichever direction you look, with a temperature of about 5 Kelvin, a few Kelvin at the time this prediction was made. And remember, let me emphasize this. The measure of a good theory is predictions. So the Big Bang has actually made these predictions about 25, 30 years before these were found. They were made in the 40s, in the late 40s. So what's the evidence? The prediction is that deuterium, helium-4, helium-3, and lithium predicted to be formed in the first few minutes. And you should see the same amounts everywhere. The first prediction, which is actually very strong, is that the amount of helium compared to hydrogen should be about 25% by mass. Clean prediction. If you didn't see 25%, there would be a big problem. In fact, in the 1950s, the first measurements did not actually show a lot of helium. And people were surprised. They said, oh, there's a problem with the Big Bang. that's where we are today. So this is the best current data. It shows the abundances. So it shows helium compared to hydrogen over here, the green line. These are the predictions from theory as a function of the density of matter. That's the amount of deuterium, the blue line. That's the amount of helium. That's the amount of lithium. And this is a function of the density of baryons, of ordinary matter, at that epoch. And of course, because it's a single universe, you should expect that the measurements of deuterium to hydrogen, helium to hydrogen, will all give the same density. You should get the same values of density from all the measurements. And these are the measurements over here. So that red circle is a measurement for helium-4. That red circle here is a measurement for deuterium, helium-3, lithium. And the beautiful thing is that they all give you exactly the same density. What is even more beautiful is that you can actually measure this density using some other techniques, using a microwave background. And that red line that you see over here, the solid red line, is a completely independent measurement of the density from the microwave background, from what's called the WMAP satellite. So what this is basically telling you is that the amount of helium is 25%, exactly what we expected. And all of these values depend on the density. You can measure these values with optical spectroscopy, and they should all give a single density. This was first done about 40 years ago. And the bottom line, the punchline of this plot is that there's wonderful agreement between the density that you measured, you inferred from the different elements. So every one of these, helium, deuterium, helium-3, lithium, they all give you a single density. And that's wonderful. It's very rare in physics if you can make a prediction 20 years before an experiment, especially in cosmology. You can actually go out and predict what happened 3 minutes after the Big Bang. 50 years after, 40 years after the first results came out, when I see this slide, I am still amazed. I mean, it's quite mind-boggling that 75 years ago, people could actually make such a prediction, that you will see these abundances. It tells you wonderful things about physics. So,
讲了一个很重要的概念，就是说一个好的理论啊，物理的理论，不单是要能够解释现有的现象，要能够预测。那如果预测后来又证明的话，这才是大胆，才是然后才能够承受得住后来的挑战。那这个在1948年那时候发表的时候，就是说，如果有一个当时很热的 Big Bang 这件事情的话，预测就会有核融合，核融合就会有这些元素的比例。那大家都知道，氢跟氢这样有可能会做成氦，所以宇宙中间是有东西做氦的。可是我们宇宙年龄不够大，没有办法做很多氦出来，所以刚开始靠大霹雳出来的这些尤其是氢的同位素氘啊，那些是核融合很难产生的，锂也是。就这些氢的周期表上前面这些元素还有同位素呢，在1948年就已经预测出来，如果当时有个很热的那个环境的话，它们应该会出现哪些比例，就这些元素的比例。那后来他这边这张图，他就觉得一直很印象很深刻，因为你把这些东西的比例算回去，说它应该发生在什么时刻的话，发现这些不同的元素，发现它的密度都是一样的，以至于在前几年，另外一个人造卫星去量宇宙维多背景辐射的那个观测值是红色的那条直线。换句话说，后面的量到元素的比例，跟量这个宇宙微波背景辐射另外一套观测的实验量到的宇宙当时的那个密度，跟理论预测值一模一样。所以这一个有高温度的核融合的这一件事情，是有大霹雳存在一个非常非常重要的一个证据。
So that's nuclear synthesis. So we have a prediction, and nuclear synthesis measurements seem to have shown the prediction is fine. So what's next? The next thing is the cosmic microwave background. And as we said, after recombination, so before recombination, there were all these protons and electrons. After recombination, extremely few electrons, and the radiation just goes away in all directions. And this is predicted to be visible as what's called black body radiation, which has a particular shape in every direction, to the temperature of 5 Kelvin. Again, 1948. And the beautiful thing is that 17 years later, this was detected by Ardo Penzias and Bob Wilson in 1965, the temperature of 2.7 Kelvin, within a factor of 2 of this prediction. And this is telling you that this is extremely strong evidence for a closed, nearly perfect, homogeneous and isotropic universe at early times. And I'll show you what I mean over here in a minute. So that's the picture that we've gotten. This is from 1992 from something called the Cosmic Background Explorer, the COBE satellite. So I said that the prediction for the microwave background radiation is that it should be a black body. A black body has a shape. So I'm plotting here intensity versus frequency. And these are measurements. These are all the measurements from this Cosmic Background Explorer. And this curve over here is simply putting the black body curve on top of these points. It's not a fit. This is the best black body we know in the universe today. Scientists spend a lot of time trying to build good black bodies, and this is a wonderful black body. I should say one more thing. The points over here, the error bars on those measurements, on these measurements, are 100 times smaller than the size of the points. So the error bars are actually shown over here. The error bars are about 0.05 or so. And you can see the points are about 200. The points are tiny. The error bars are tinier. And this matches the black body wonderfully. It's just a